Welcome back to the course entitled Chemical Crystallography. In the previous lecture, we have discussed about how to deal with a dynamic disorder in perchlorate anion, and we started talking about how to deal with a static disorder in perchlorate anion. Actually, the perchlorate anion, which we know is tetrahedral in shape, and the way I am drawing is, of course, familiar to you, that the oxygens, these two oxygen atoms and the chlorine atom are on the plane of this projection, and these two oxygens are up above and below the plane. So in case of a dynamic disorder, these oxygen thermal ellipsoids will be very elongated, large, and this disorder will slowly reduce, and at much lower temperature you will be able to confine these atoms at its location. But the case is not always as simple as this. So in case of a static disorder, it may so happen a perchlorate anion is present at two different locations with different occupancies. So maybe perchlorate anion at this location, which we mark it as suppose 1A, and oxygen 1A, 2A, 3A and 4A. Here it is maybe 60%, and there 1B is about 40%. For B. So how to deal with this static disorder? You see, different anions can cause this type of disorder. The examples are ClO4, different types of anions can cause this disorder, like ClO4 minus, BF4 minus. You see here the anion has very high electronegative elements associated with the central atom. One more kind of static disorder one may encounter is this one. So boron is disordered at two different locations. This fluorine is disordered at two different locations. This fluorine is disordered at two different locations, whereas this fluorine and that fluorine is located at one position of their own and is shared by the two boron atoms on either side. So there are different scenarios of the static and dynamic disorders that can be present in a crystal structure with this type of anions. So let us take the example of a BF4 minus ion, where you have two such BF4 ions. One BF4 ion minus ion has a dynamic disorder, and one has a static disorder. What does dynamic disorder mean? This disorder is related to the temperature of data collection. On lowering the temperature of data collection, this dynamic disorder slowly reduces, and at a lower temperature like 100 Kelvin, it nearly disappears. Whereas the static disorder is something which does not depend on temperature. On lowering the temperature, the thermal parameters, thermal ellipsoids of the atoms associated with the disordered part reduces, but they don't completely resolve. And these disordered portions appear as at two different sites in the unit cell. So let us take the example. We write BF4 at two different locations. So I write it as B1A with F1A, F2A, F3A, and F4A. And another location is this one, B1B, F1B, F2B, F3B, and F4. So these are two distinct coordinates of all the 5 atoms that are associated with this amine. So remember, we already have this dynamic disorder. So we should treat this dynamic disorder as, suppose, part 1 and part 2, and we assign the occupancy parameter as plus minus 21.00 as we had discussed in the previous class. So now in today's class, we will talk about the static disorder, how to treat this. So this static disorder part, we write it as this part as part 3, this part as part 4. So in part 3, we should arrange these atoms in the sequence B1A, F1A, F2A, F2B, F3A, F4A, and we close it as part 0. So these will have the corresponding x, y, z coordinates for all of them, different of course x, y, z coordinates, and we assign the occupancy factor as plus 31.0 for all of them, and we assign a starting isotropic thermal parameter which is written as U iso, or the isotropic thermal parameter to start with as 0.05. Then we write, so this is part 3, we write part 4 and write the coordinates. These are written in the INS file. So B1B, F1B, F2B, F3B, and F4B, and then at the end you write part 0 below that. So this will have some set of coordinates z prime for all of them, and the occupancy parameter will be minus 31.0 for all of them, and U iso as 0.05. So now what we see that these atoms do not share any common atom. So there should not be any EXYZ command for this. No EXYZ. Simply because none of these atoms share coordinates. But For the easy understanding or for easy refinement of the structure, we should use EADP command for those atoms which are similar. So we should do EADP B1A is same as B1B, EADP for F1A same as F2A, sorry, F1B, and like that EADP for F2A is equal to F2B, and all of those. So this will ensure that the thermal parameter of this fluorine and thermal parameter of this fluorine are approximately to be the same. So with this, you should use the command fvar as 0.5 to start with, which indicates that plus 31 means 50% occupancy, minus 31 also means 50% occupancy. So when we refine this structure with these commands, what we will see is that the f var parameter changes to something like say 0.72, indicating that the part 3 is 72% occupied and part 4 is 1 minus 0.72, that is 28% occupied. So this way we can identify what percentage of two different locations are occupied by the BF4 minus anion. So by doing this refinement, one can treat the dynamic disorder in case of BF4 minus, ClO4 minus, or as such in any other molecule which may be disordered at two different locations. For example, sometimes we encounter solvent molecule like toluene, which also is found to be disordered at two different locations. As a result, we have to do this kind of refinement on all the atoms of toluene and find out what is the final refined parameter for that disordered fraction. So once you complete this refinement, then you will see that these U-iso values are also getting refined. And it takes some reasonable value, which may be something like 0.0232, 0.0242, like that. All will have very similar U-iso parameter. So once the refinement has converged, then we should of course do anisotropic refinement by incorporating the command anis in your INS file. Or if you are using OLEX2, you can simply click on the ellipsoid button. It will do the anisotropic refinement of all these atoms which are now disorder treated and are refined to a reasonable isotropic thermal parameter. And then we should take this and complete the refinement following the standard procedure that we have already discussed in one of the lectures. Let me just introduce you to a different type of static disorder. Static disorder in fluorophenyl ring. Suppose you have, I am taking a real life example. You have one molecule which has a phenyl ring here and a phenyl ring at this point with a metafluoro position. What we have observed is that this CC bond is flexible. As a result, this particular phenyl ring in the structure appears as this, with the molecule connected upwards, and appears as that with the molecule connected upwards. So that means the fluorine appears on either side of this thing. So as a result, what we see in the structure as an average, that fluorine appears here, fluorine appears there, but the CF bond length, which ideally should be equal to 1.36 angstrom, is deviated to like 1.21 angstrom and 1.18 angstrom, which indicates that there is something wrong in these positions. So then what one has to do is to treat these two groups separately. So if I name those atoms as C1, C2, C3, C4, C5, C6 and F1 and F2, what we should do is to do a split command on all the atoms C1, C2, C3, C4, C5 and C6 and press enter in OLX 2. What it will do is it will generate two atoms at the same location with names C1A and C1B, C2A and C2B, so on up to C6A and C6B. So then what we should do is to segregate these two sets of A's together and the B's together and take the corresponding fluorine in it together. So we write a part 1 as C1A, C2A, C3A, C4A, C5A, C6A and F1. We call it as part 1 and it will have its corresponding XYZ. Then we say it is class 21.0 and we give the thermal parameter 0.05. So for all that we will have different coordinates. All will have a class 21 as occupancy parameter and 0.5 and then we close it as part 0. Similarly, write part 2 and include C1b, C2b, C3b, C4b, C5b, C6b and F2, all that with 0.05 as thermal parameter. So this will be the minus 21 as the thermal parameter. So what will happen is now we have two parts, part 1 and part 2. But you see that the atoms C1, which is split as C1A and C1B, they are located at same place. C2A and C2B are located at same place. Like that, C6A and 6B are located at same place. So we should have EXYZ command for C1A, which is equal to C1B, and should have it for all of them from 1 to 6, indicating that they are at same coordinate. And also, for simplicity of the refinement, we should also use EADP for C1A to C2A, C1A and C1B up to C6A, C6B, and also F1 with F2. So if you do this and then do the refinement with a value of f var as usual as 0.5, it will then refine to a reasonable parameter and will tell you what percentage of the molecule has fluorine on the right hand side, what percentage of molecule has fluorine on the left hand side. So this part 1 and part 2 process has to be applied as it was done in case of BF4, but here we add extra EXYZ for the carbon atoms which are located at its original position even when it is disordered, which essentially indicates that the molecule has only rotated about its axis like this, keeping all the atoms in the plane same, but this fluorine atom which is here gets rotated to the other side like this. So this rotation is allowed. We are assuming these carbon atoms which are on the plane of the paper or in the rotational plane, they are at EXYZ, means they are at same point for each and every atom corresponding to those carbons. So then when you do this refinement, you will end up getting this FR value refined to maybe 0.75, which will indicate this as 75% and that as 25%. So this will then conclude the status of disorder in these type of molecules. So after a refinement of 10 to 20 cycles, this FR is refined and converts to a number, and once that has converged, then one should try to do the anisotropic refinement on that thermal parameter, which initially we took it as U iso. So you do this anisotropic refinement with the command anis. So this single thermal parameter will then expand to 6 thermal parameters, and the molecule, the atoms, all of those will look like ellipse, and those ellipsoids should not look elongated, flat, or like a pyramid. If some such things happen, then we need to address those issues and try to see how those can be made elliptical. So this process that we have discussed today in this class will be demonstrated in the following lecture with an example data using OLEX2. So till then, thank you. I hope you are enjoying the course and you will learn how to do this using a software in the next class. Thank you.